In this video, I'm going to go over two things. One is the activity series, and the other thing is solubility charts. The activity series I'll do first. Now, this really only comes up when we're talking about single displacement reactions. And the activity series, different ones might look slightly different. The one that I have on the screen here, it has a little bit of an indication of how these things actually react depending on what you're trying to react them with. A lot of activity series just have a listing of the elements in a certain order. And this one has actually nonmetals to halogens at the bottom. Not all of them have that. Some of them are just metals. But they're all pretty much used the same way. When you have an activity series, the most reactive metal is going to be at the top, and then as you move down that column, they're going to become less reactive. The other thing that varies a little bit is on some reactivity series, if you look up online or whatever, they might have an arrow pointing down that says decreasing activity or reactivity. And there might be some that have an arrow pointing up, they say increasing activity. It's really all telling you the same thing though. The most reactive metals are at the top, and as you go down the column, they become less and less reactive. Now again, this is specifically for single displacement reactions. So I have two examples here. And when you look at this on paper, it makes it seem real easy, like everything's just going to happen. You always get a reaction, but that's not always going to be the case. What you want to remember when you're looking at a single displacement reaction, the more reactive element is going to be the one that ends up in the bottom. So what we have to look at is the zinc is going to have a tendency to replace that copper. But what we have to do is use the activity series and see if the zinc is reactive enough to take the place of copper. So what you want to do is you find those two elements. There's zinc and there's copper all the way down at the bottom. Zinc is more reactive. So that tells us that zinc would be reactive enough to replace copper. Now when you write out the products, remember we're talking about ionic compounds here, so we have to pay attention to the charges. Zinc is a positive 2. Sulfate has a negative 2 oxidation number, so you get ZnSO4. Now copper ends up getting kicked out of that bond, so it's by itself. It is not diatomic, so you do not write any kind of subscript there. And now since it's by itself, you don't even have to worry about oxidation numbers because it's not bonding to anything. And then when you're done, make sure you balance anything you might have to balance. And this one looks like it's balanced. There's zinc on each side, copper, and sulfate group. So remember, the more reactive element is the one that's going to be in the bond. So now what we have to do is see if, in the next example, if silver is reactive enough to displace or replace iron. And so we want to pay attention to where they are. Silver is all the way down here, and iron is here. So what it's telling us is iron is the more reactive metal out of the two. So silver is not going to be able to replace iron. So what we would just put here is no reaction. If you took a piece of silver, you put it in iron 2 sulfate, nothing's going to happen. It's just going to sink down to the bottom. All right, so remember, the main thing, the more reactive element is going to be the one that is in the bottom. Now you can also do some examples with the halogens, where one halogen might replace another, but it's the same general idea there. All right, now one that's takes a little bit longer to explain is the solubility chart. Now for us at the 5.0 level, I would just give you this solubility chart. You're not expected to memorize this. Just like with the activity series, you're not expected to memorize that. We would give you the chart. You just have to know how to use it. If you take honors chem, or if you go on to Chem 2 or AP Chem, or if you take chem classes in college, you might be expected to memorize the rules that help develop this chart. But for us, we give it to you. Now there's really, I think the most common mistake people make when they're using this chart is we have these letters here. Mostly what we're going to work with is either going to give us S or I on this chart. S means soluble. So when you write out a chemical reaction, if something is soluble, you do not write a little S after it, because that actually means solid when you write out a chemical reaction. If it says soluble here, what that means is it's going to be aqueous, and you would use the abbreviation of AQ. Now if it's insoluble, like if you put sand into water, it's insoluble. That, if you write out a reaction, if something is insoluble, that's when you might put a little S in parentheses after it saying that that stuff remained a solid or precipitated out of solution, whatever the case may be. So I'm going to look at this example down here. Barium chloride and is reacted with sodium phosphate. Now, when you look at reactions like this on paper, it makes it seem like no matter what, a reaction is going to occur. And that is not always the case. So what I want to do is start off figuring out what barium chloride are and what sodium phosphate, what barium chloride is and sodium phosphate is relative to their solubility. So what we do is we find barium, we go over to chloride, which is right here. And that has an S. And remember, this is where people make a mistake if they're going too fast. If you have an S there, it actually means aqueous. It means it is soluble. Now, if you found sodium, and for us, so I don't have to keep scrolling up and down, sodium phosphate would be this one right here. So that is also soluble. So we would put aqueous with that one. Now, what that means is if you put barium chloride and sodium phosphate into water, they will dissolve. If you're doing a reaction like this, you would never just take solid barium chloride and solid sodium phosphate and mix them together. Nothing would happen. They have to be dissolved in water because that is when they are going to dissociate into different ions. So what you're going to have is barium ions, chloride ions, sodium ions, and phosphate ions. Basically all floating around in that solution, in that beaker. Now, for a reaction like this to occur, we know that the cations from one compound are going to form a product with the anions from another one. But really, for that to happen, one of the products is going to have to be insoluble. So what we want to look at is barium reacting to phosphate. Is that going to give us some kind of insoluble thing, a precipitate? So we find barium, we go over to phosphate. Now that says I. So what that's telling me is that when we have this solution, the barium and the phosphate are going to form an insoluble compound. And they're basically going to fall out of solution. So they're not going to be available anymore. So when we write this out again, pay attention to the oxidation numbers. You have Pa3, PO4, 2. Now, when you're writing this out, you have a couple options because this is on the product side. You can either use an S if you want to, saying it's solid. You could put a down arrow, that means it's forming a precipitate. Or you could write PPT, which is just short for precipitate. So that's telling me that if I did a reaction with barium chloride and sodium phosphate that were in the aqueous phase, or aqueous state, we would get a reaction where barium phosphate falls out of solution. Now the other thing we have to check, and this one should be obvious, we have sodium bonded to chlorine, which is just table salt, and if you check the sheet, sodium chloride is going to come up as soluble, which is what you'd expect for table salt. Okay, I lost what I was writing. So what we're going to get, there we go, is sodium chloride that is soluble. So if this thing starts to work, we would write NaCl. You would just put an AQ in parentheses after it, and that's how you know that that reaction happened. One of those things ended up precipitating out. But remember, whenever you do this, a lot of times when you're going through all these things, you forget about balancing if you're going too fast. So there's 3 barium, so I'll balance the barium. Now that gives me 6 chlorine, so I need a 6. That gives me 6 sodium, so I can put a 2 here for 6 sodium, and then that takes care of the phosphate group too. Alright, so we predicted the products. We know the reaction will happen because we get a solid precipitate. We wrote the aqueous symbols for all the other things, and then we balanced it. So that is activity series and solubility charts.